Now that we've introduced Laplace transforms, let's go ahead and put those Laplace transforms to good use and connect them to differential equations by solving some initial value problems. We're going to need to review some partial fraction decomposition, but then we'll use those to solve some differential equations. So let's quickly remember how to do partial fractions if we have distinct linear factors. So if we have 3 over x minus 1 times x plus 2, we break this down into his two component pieces. It's like unadding the fractions, okay? And then we can get a common denominator. And then if that's true, then the numerators have to be the same. Okay. And we can use some substitution here to help us out. So if x equals 1, then 3 is equal to a times 1 plus 2, or 3, so that a would have to be 1. If x equals -2, then that's what would make this term be 0. We'll get 3 equals b times -2 minus 1, which is -3, and so we'll find out that b is -1. Okay. So what if instead of having linear factors like x minus 1 and x plus 2, what if we have quadratic factors? So we've got x squared plus 4 and x squared plus 1 here. We're going to do a similar process, but when we break these guys up into proper fractions here, for this to be a proper fraction, the numerator needs to be a linear factor because the denominator was a squared factor, a quadratic factor, and same thing here. So let's use our partial fractions to decompose this guy. Just like we did above, we'll get a common denominator and then equate numerators. So doing that, we get 2 equals as plus b times s squared plus 1 plus cs plus d times s squared plus 4. Okay. And again, we have several choices. We could distribute through and then work on him. In fact, that's what I'll choose to do here. So 2 is equal to as cubed plus as plus bs squared plus b plus cs cubed plus 4cs plus ds squared plus 4d. If we write this as 0s cubed plus 0s squared plus 0s plus 2 on the left-hand side, and if we group on the powers of s here, so we'll have s cubed, and then I like to underline them to make sure I haven't forgotten anybody, a plus c plus s squared times b plus d plus s times a plus 4c, and plus our constant terms, which are b plus 4d. Okay. So that sets up for us a system that a plus c equals 0, b plus d equals 0, a plus 4c equals 0, and b plus 4d's equals 2. Okay. We can then put that into a matrix. Let's do that really fast. So let's matrix edit. So this will be a 4 by 5 matrix with coefficients of 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 4, 0, 0, and 0, 1, 0, 4, 2. Okay, I'm just going to do a quick double check, make sure that all of my entries are correct. And then if we do some matrix math on that matrix, we find out that A equals 0, B equals negative 2/3, C equals 0, and D happens to equal positive 2/3. So that means that 2 over the quantity s squared plus 4 times s squared plus 1 is equal to negative 2/3 times 1 over s squared plus 4 plus 2/3 times 1 over s squared plus 1. Substituting in the values for B and D and A and C, of course, but those were 0. Cool. So now let's do a quick review and then we'll tie in the Laplace transforms. So let's take and solve this differential equation, x double prime plus x equals sine of 2t, with the initial conditions of x of 0 is 0 and x prime of 0 equals 0. And we're going to do it without Laplace transforms, and then we'll come back and do it with Laplace transforms so we can compare. Well, first off, we take a look at x double prime plus x equals sine of 2t, but that's a non-homogeneous equation, so we'll do the homogeneous first. We notice that this is a second order constant coefficient linear differential equation, so we expect the solution to be x of t equals e to the rt, something like that, which gives us a characteristic equation of r squared plus 1 equals 0. So that would mean that r squared equals negative 1 and r would equal plus or minus I, which is 0 plus or minus I. So our roots are complex conjugates. Therefore, we will find out that x of t is equal to c1, well, e to the plus or minus it, but we can find out that this is going to, using Euler's identity, give us c1 cosine of t plus c2 sine of t. Okay. So we now have solved the homogeneous case, so this is our complementary solution. Now we see that he has a non-homogeneous piece, sine of 2t, and we notice that sine of 2t and his derivatives, so let me just write that down. So f of x equals sine of 2t. His derivatives are going to involve sine of 2t and cosine of 2t multiplied by constants. So we would expect our particular solution to look like a times the sine of 2t plus b times the cosine of 2t using the method of undetermined coefficients. You could use the method of variation of parameters if you'd like. Now, we notice that there's no duplication in our particular solution with our complementary solution, even though they both involve sine and cosine, but this is t and these are two t's and those are different functions. So let's go ahead and see if we can figure this guy out. So xp prime would be 2a cosine of 2t minus 2b sine of 2t, and xp double prime of t is going to be negative 4a sine of 2t minus 4b cosine of 2t. Substituting those guys into our original differential equation, we'll find out that negative 4a sine of 2t minus 4b cosine of 2t, and that's xp double prime, plus x of p, which was a sine of 2t plus b cosine of 2t. And let me label those for just a second. So here's x sub p, and here's x sub p double prime. Those need to equal our original non-homogeneous piece, which is 1 sine of 2t plus 0 cosine of 2t. And let me pause right there so we keep our videos at about 10 minutes. We'll pick up with the rest of that guy in the next video.